And
Yes, I am recording this and we're going to make sure that people get them. Okay, so
thank you.
Xavier, you can share your screen and begin. And I'm starting my timer.
Can everybody see my screen?
Yes, we can.
Awesome. Thank you. I appreciate it. Good afternoon, everyone. My name is Joshua Xavier Backus, and today I'm honored to walk you through a project that is close to my heart, the Daedalus Suite, a suite of AI systems designed to reimagine how hospitals function, support staff, and most importantly, care for patients. I can't do that. Okay, navigate forward. There we go. Here's a quick overview of what we'll cover. We'll start with the why this project matters. Before diving into the what and how, I'll walk you through each system, the research behind them, and the implementation, and ultimately what this could mean for real-world healthcare. In the healthcare industry, I've seen firsthand the toll burnout takes, not just on staff, but on patients and outcomes. Between data overload, delayed responses, and resource limitations, hospitals are constantly being asked to do more with less. This project aims to change that with the help of integrated intelligence systems. The problem is multifaceted. Overwhelmed staff, delayed emergency responses, and inefficient allocation of resources. So we ask, what if we could deploy a network of AIs, each with a specialized role to work collaboratively and lighten the load? The result is the Daedalus Suite, made up of 4 interlinked systems targeting staff wellness, triage, patient monitoring, and resource distribution. Now, beyond the tech, this project is deeply personal. Like many of you, I've watched loved ones navigate care systems that are often reactive, not proactive. This suite is built from a simple motivation to make hospitals not just smarter, but more humane, more responsive, and more compassionate. We've come a long way from paper charts. Yet, despite digitalization, integration, and real-time intelligence are still sorely lacking. AI has matured, but the challenge is no longer just accuracy. It's about delivering the right insights to the right person at the right moment. Research in this space shows enormous potential, but also reveals serious limitations. We have brilliant AI tools, but they rarely survive the jump into real-world hospitals due to ethical gaps, legacy systems, and siloed data. What we need is coordinated intelligence that works with existing infrastructure and respects human roles and responsibilities. That's what the Daedalus Suite is designed to do. Ethically, people are worried about stealing data and not adhering to HIPAA and current policy standards. The Daedalus Suite only uses the device ID in the rooms that are already there, just makes some modifications, and data is ready to be fed into the AI suite. There's integration issues, there's emergent trends, shifting towards operational intelligence, integrated platforms. There needs to be integration guidance, comprehensive evaluation, and ethical guidelines. This is not a replacement for doctors and nurses and staff. This is a tool to extend to doctors, nurses, and staff to make their job better for us. For the system, I took a modular approach. Think of it as 4 specialized AIs, each trained for a specific mission, but all working in sync. We named them Heka, Hygeia, Isis, and Eunomia, drawing inspiration from mythology to emphasize their purpose: to protect, heal, prioritize, and restore balance. Each AI tackles a specific domain. Hygia monitors staff health in real time, making sure our caregivers are also being cared for. HECA watches over patient vitals to spot problems early, sometimes before they even arise. ISIS is our triage brain, matching patient needs with the most appropriate and available professionals. And finally, Eunomia optimizes bed assignments, staffing logistics, and equipment usage. All four systems talk to each other. When a nurse is exhausted, ISIS knows not to assign them high acuity cases. When a patient condition deteriorates, HECA alerts Eunomia to adjust the resource map in real time. It's orchestration, not automation. I followed a clean 3-layer architecture: acquisition layer for gathering data, processing layer where the AI lives, and the application layer which presents insights to the people who need them. This separation helps with scalability and compliance while making the system transparent and trustworthy. I've implemented everything using agile cycles, constantly refining based on feedback. The suite is containerized, CI and CD enabled, and built for real hospitals. This isn't just a proof of concepts, it's a prototype that can be deployed and adapted. Sorry. I've leveraged the best tools for the job: Python, React, Kafka, TensorFlow, and more. And yes, interoperability and security were paramount. I followed the HL7 FHIR standards and ensured HIPAA compliance across the board. There was a message. I don't know how to see it. I'm so sorry, Jeff. I generated synthetic data for all systems, enough to simulate thousands upon thousands of scenarios while preserving privacy. HECA pulls vitals like heart rate, blood oxygen. Hygia reads from wearable devices like your Apple Watch or your Fitbit. ISIS cross-references severity and skill. Eunomia tracks hospital metrics like staff availability and bed occupancy. All of it was linked with realistic time patterns. Talking about the synthetic data and the data integration, I used a robust ETL pipeline to clean, tag, and align the data. The models don't just predict, they explain, prescribe, and evolve. I approach this from 4 lenses: descriptive, diagnostic, predictive, and prescriptive. I didn't want black box results. I wanted explainable AI that supports human judgment. Descriptive analytics, talking about what happened, the statistical characterization, and distribution analysis. Then we go into diagnostic analytics. Why did it happen? That would include feature importance and correlation analysis. Then we go into predictive analytics. What will happen? This is classification and forecasting, also anomaly detection. And then prescriptive analytics, which is the top level. What should we do? Optimize algorithms and intervention recommendation. Now, here's where it gets exciting. When these AIs work together, hospital efficiency could increase by 28%. Emergency response times can be dropped by over 4 minutes. Staff burnout can be reduced by 39%, and operational costs can be decreased by 15 to 20%. And that's just with synthetic data. With real-world deployment, the gains could be even higher. Do not get the wrong idea. This system is not to take over the healthcare industry. It is used as a tool that doctors and nurses can use to make faster judgment calls and optimize treatment. It is not a replacement. It's an extension of care. So, where do we go from here? Well, as exciting as our 94% accuracy and 28% efficiency improvements are, I'll be honest with you, Right now, the Daedalus Suite is like a really impressive car that we've only tested in a simulator. It's time to take it to the real track. My immediate priority is moving from simulation to reality through clinical validation. Think about it. We've proven the concept works with synthetic data, but real hospitals have messy, unpredictable data, and that's exactly where we need to test. On the technical side, we're not just trying to make it work, we're making it work safely. Edge computing will let us process critical patient data in milliseconds, not minutes. And our cybersecurity framework, well, let's just say HIPAA compliance isn't optional when you're dealing with real patient lives. Now, here's where we get strategic. We're not going to walk into a hospital and say, hey, let our AI manage our most critical patients. Instead, we start smart. Resource allocation first, because that's lower risk, but high impact. Then staff assignment, and finally, the high stakes patient monitoring. The timeline, 12 months to get through regulatory pre-submission, 18 months to our first pilot, and within 2 years, we'll have real clinical validation data, not just simulation, real data from real patients getting better care. But let's dream bigger for a moment, because what I've built isn't just a hospital management system. It's the foundation for something much more transformative. Picture this. Our current 4 AI components become 8, and then 12. We add clinical decision support that can help a resident doctor in Mural, Montana access the same diagnostic insights as a specialist at Johns Hopkins. Communication optimization that ensures critical information never gets lost in the shuffle, and predictive analytics that don't just manage current patients, but help prevent disease in entire populations. We're talking about precision medicine, where your AI assistant knows not just your symptoms, but your genetic predispositions to medications. Multimodal monitoring that can detect a stroke risk from subtle changes in how someone walks down a hospital corridor. And yes, quantum computing to solve optimization problems that would take our current computers years to figure out. But here's what gets me really excited: the global impact potential. We can adapt this for a clinic in rural Kenya just as easily as a major medical center in New York. By contributing to open source standards, we're not just building a product, we're building a movement. By 2027, I envision multi-hospital networks sharing AI insights across cities. By 2030, I want to be leading the conversation on international healthcare AI standards. And by 2035, partially autonomous healthcare facilities where AI handles the routine so humans can focus on what they do best, caring for people. We started with 4 AI components in one hospital. We're ending with a blueprint for transforming healthcare globally. That's the journey from integrated AI suite to healthcare revolution. The Daedalus suite shows what's possible when AI doesn't try to replace healthcare professionals, but instead augments them. It supports the people who support us, our nurses, doctors, techs, and staff, while ensuring patients get timely, attentive, and personalized care. And that is my presentation. Is there any questions?
Okay, you've got
Thank you
5
so
minutes.
much. Oh, sorry.
Oh, you're there, Anna. Okay, go ahead.
Yeah, I'm here. I'm back. I'm so sorry. Thank you for your patience, and thank you so much, Xavier, for your presentation. It was great. And yeah, now we have 5 minutes for questions. So please raise your hand if you have any question.
Yes, Morgan?
Okay, so one of my questions is, how are you going to collect the data that determines staff burnout?
So the data will be provided by items like Apple Watches, your Fitbit, because I know in this day and age, a lot of nursing professionals and doctors have those types of wearable devices. So it will be like in later development, there will be an app that comes with it for doctors and nurses within the hospital. So this is like a closed network kind of thing. And that data will be fed from the Apple Watch. So it will focus on stress levels like heart rate, how many times they've had a break, and it will reward them for taking breaks as well.
Yeah, right. And you're going to measure
I'm sorry, what?
you're going to measure steps.
Yes.
Okay, I don't know.
Everything that the Apple Watch and Fitbits carry, they will track as well.
We'll have to talk about that. I don't know how good a job it'll do to measure all levels of stress.
Yeah.
Okie. Yes, Miss Robinson.
Yes. Question. I know you
Yes.
use synthetic. I know you use synthetic data right now for this, but going into real time into a hospital, how do you propose to take care of real data? All this data, unstructured, structured data that is flowing through the hospitals. How do you propose to take that data and I would say analyze it and structure it in a good way for tagging and labeling it so it can be utilized for what you're trying to do?
So before implementation of any AI, you are going to pretty much outfit the hospital already existing architecture with like bed number, what device is in there. You'll record all of that. And then once all of that is recorded, then it will be applied to the AI system. So we're not taking any patient data. We're not taking we're not violating any HIPAA laws, and making people feel safe. So it's only going to take data from like the heart monitor, a weight sensor. It'll take metrics from the bed, from your temperature, from your blood oxygen levels, and then it will take that randomized data and funnel it to a patient ID. I say patient ID, but it will be connected to the room and so the room will get a serial number. And then after it's being fed, all four AIs will be connected to each individualized room. Now,
so how are you going to keep these AI modules from hallucinating?
hallucinating?
Yeah.
They can't hallucinate.
Excuse me?
They can't hallucinate.
Okay.
What do you mean?
Look into that. Look into that.
I'm gonna look into that.
Yeah. Model hallucinate. Okay. But that was good.
Oh, okay. And you're saying, how do we misleading?
Yeah, how you have to test, you have to do a testing and validation and monitor that so they won't hallucinate. And
of course.
And how you train your models is you keep from, ensuring that they don't. And you're talking about deploying 4 for this
within a subset of servers. This is going to be an all internal kind of thing. So the AIs will be on premises instead of like from a cloud, or because then that's just dangerous.
Okay, I think the 5 minutes for questions is over. Now it's turn for Matthew.
Thank you.
Thank you.
And can you hear me? Just checking my audio is working.
Yeah.
Great.
Yeah, I can hear you.
All right. Great. Hi, everyone. My name is Matt Emerson, and today I'm going to be presenting about minute-level electrical load forecasting in the city of Los Angeles. And we have an agenda. Should look very similar to what you have just seen. So starting off, the problem is that current electrical load forecasts are typically produced for hourly or quarterly timescales, not more granular timescales. And these tend to focus on the overall system and not specific assets that are more granular, such as at the transformer level. So as we are moving forward into transitioning to a carbon-free electric grid with a lot of new diverse generations, such as solar panels and wind turbines, it's becoming more important to have a more granular forecast. So we all can recognize that electrical power is essential. We absolutely need it for our modern life. We would not be here having this meeting without electrical power. And the grid has drastically changed and is continuing to drastically change. And with that change, the industry is also seeing the load demand shift and change shape over time. So one of the goals here is to make sure that there are accurate forecasts to meet the demand that is present. Some background on this. I chose to do study Los Angeles, partly because they are a public utility, and as a public utility, they tend to release a lot of data, which is convenient. So they have a strategic long-term resource plan that they've released. It provides guidance on how they are looking at load forecasting and the challenges that they're foreseeing, so we can fold that into my study. I also found a really interesting book on it. It probably would bore most people to death, but I kind of read it cover to cover. So we all have our own particular interests. A lot of other work has been done on predicting electrical load, but most of it does tend to be either hourly or at 15 minutes at most. And the other interesting thing that basically the power grid designers of previous years did not consider is the grid is becoming bidirectional. And it used to be that we just had customers and they would pull power off of the grid and it would be more when it was hot or more when it was cold. But now with solar and electric vehicles, it's really becoming bidirectional, and it's causing some interesting problems at the lower levels of the grid. So to approach this topic, I decided to work on 1-minute forecasts over a 24-hour period. And I wanted the forecasts to be accomplished in less than 5 minutes. So basically the model should run in less than 5 minutes. And then targeting an overnight retraining time of less than 4 hours, and mean average error under 5%. Also being able to tolerate data failures. Some of this data, as you start getting into the edges of the grid, becomes less reliable and more likely to have periods where it wasn't communicating or was not recording. So ideally, the model should be able to accommodate that. The data starts off with 1-minute megawatt readings. I originally had 4 transformers, but I scaled up to all of the transformers that Los Angeles provided me. Used a service called Open Medio for weather data because they enable grabbing historical data back for years and years, which is very useful. And then added some lags, data lags, and some time encoding, such as what day of the week is it, what hour of the day is it. Also became interested in this concept of a cooling degree day because it allows for covering thermal inertia. Basically, as it gets hot and stays hot, houses tend to use more power. So you need to capture that over time, is that on the second day of a heat wave, they'll use more power than the first day. And then on the third day of the heat wave, they'll use even more power. And had to also implement some clipping of the outlier data. You'll see some pictures here in just a minute. It's quite a bit of interesting data. For the models, use a random forest model as kind of a simple, easy to run, easy to train, quick model. And then went to some more temporal models from the LSTM, the TCN, NBEATS, and temporal fusion modeling. I saved about 1 million plots and various metrics and copies of each of the models, so I could actually rerun the model later using Python and some various standard neural net libraries for Python. To get my data, I actually filed a public records request with the Los Angeles Department of Water and Power. They did get me all of the data, covering 69 transformers for basically a 5-year period. If anyone's curious, that's a lot of data. It was 800 megabytes of compressed CSV files, so quite a bit of data. And then there had to do some quality checking. So wrote a Python script to check that data, do some various flagging of bad data, and look for anomalies in that data. So total ended up being 283 million records covering the 69 transformers, and then 3.2 million records of weather data matching that sort of time frame. And this is one transformer and all the data. And you can see that the transformer sometimes gets switched off for maintenance, so it goes down to 0. And then other times it's rather high, all until the data is very spiky. I also enjoyed the scatter plot, which is colored by the year that the data was done. And you can kind of see how, there's some years where the shape of the data, the shape of the loading profile is actually different, which does validate the fact that you need to kind of continuously update these models. You can't just run a model in 2025 and expect that it's going to work in 2027. So touching a little bit more on just the data, did some statistics on the data, looked at the mean of various transformers, the median, the maximum load. This is the raw data, and you can see that here some of the data went down negative. That actually is indicative of kind of data problems or quality problems. These transformers currently do not go backwards. I also ran the same statistics after cleaning the data, and here you can see the clean statistics. All the transformers are now showing positive only loading. All of the numbers changed just a little bit as bad data was clipped out of the model. With the statistics, I got a correlation heat map, and so this is showing the different correlation values. I could either present it as a very boring table or this kind of cool looking picture. But basically, you can see that there are 4 transformers, A, B, C, and D, and they are correlated very well to each other, which does not do me really any good because I'm trying to forecast their loading. So I can't look at the transformer next to it because I also don't know its loading in the future. But instead, it does show that temperature has good correlation. The cooling degrees had good correlation. Solar radiation has some correlation. And then there's actually some interesting negative correlation with humidity. I do want to geek out on this more because this is Los Angeles. Maybe this will change elsewhere where it's more humid than it is here. So kind of some interesting results. The utility industry isn't really known for getting very advanced into computers. They don't typically have high-end GPUs. So all of my models were actually trained on just normal CPU, assuming that the utilities haven't purchased high-end GPUs. When I started off doing my training, I quickly found out that it was a terrible idea to do temporal fusion transformers. Each one of those was taking 12 hours to train, where my other models were taking between 15 minutes and a couple hours. So that was in no way going to meet the training time requirements. I also had some interesting results with the random forest model. It tended to just sort of flatline. And so that ended up sort of getting tossed out because I could not get it to really produce a reliable set of data. This isn't really surprising. Random forest isn't known for being a great temporal model, but I'll show you later there actually is some hope for it. Finally, the 3 temporal models are what I really focused on. I did eventually find out, though, that I could not on my home computer do minute level forecasting. I was going to run out of time and I would never finish anything. So I did have to switch to 5-minute intervals instead of 1-minute intervals. I ended up training successfully 149 total models. That's like 2.5 weeks of my computer running full speed, 24/7 all the time. So I'm happy with the results. Here you can see some of my results. The blue is the actual load on the day, and then the orange is the predicted load. And you may notice that this is a random forest model, which I said I didn't really do, but I got distracted and I started doing a lot of hyperparameter sweeps. And I actually found that there is maybe some hope for random forest if you sweep enough hyperparameters. Interestingly, I had to go very light on the number of passes and very light on the number of branches. When I went too deep, it actually did a lot worse. So there's room to explore there. Here's a LSTM forecast, and you can see the forecast is fitting the curve of the load very nicely. And this would be, I would consider to be a good forecast. I included this one because this is absolutely terrible. And really what I wanted to show here is I made an error in my modeling. For the TCN, I added some padding for the areas where it didn't know, where it was future data and it didn't know. And I kept on adding padding, apparently. I basically added padding in a loop. And what ended up happening is the data that was being fed to the model had a lot of zeros. And those zeros started influencing the model, and then it started putting out this, whatever this is. There are good examples of TCN. I did fix it, but I thought I would include, it's always a learning process. And then the NBEATS model, which is actually specifically built for sort of forecasting temporal data over time, also was able to produce results that were very valid. In the end, this is the metrics for my various models and the numbers for my various models. You'll notice the model numbers are not all equal. That is something I have to investigate. It looks like some of my models just failed to run under certain scenarios. The values that I found the most useful ended up being the mean absolute error, and then also the R-squared values. With LSTM and TCN coming in and being my favorite models, mainly because they train in about 30 minutes, and this NBEATS model actually takes a long time. It takes about 3.5 hours. So it didn't produce very much better results, but I also ran out of patience trying to tune the hyperparameters. So maybe with some more time. One of the main things I learned is I probably could have done this over about 4 capstone courses. I had enough data and things to do. In conclusion, I did find that and believe that minute level forecasting is both possible and would provide value. I also would say that the LSTM model performed best with TCN being right there. We're talking decimal places, so it's hard to say which one is better. You would need to spend some more detailed time, probably a year or two of good data or a lot more processing power than I have available. It did also present a pretty good fallback. I looked at some days where we had poor data or missing data, and the models did seem to perform well for that. I do have a short demo, so hopefully this plays. Can you hear the audio?
No,
Okay,
we
well,
can
I'm just
hear you.
gonna go over then because I don't have time to spend going it. So here's some of the code for the models, and this is basically my project, and each of the models has a set of code associated with it, but they all work off of a main sort of helper file, and this helper file has things like the lag times, the number of CPU processes to use, and then the various functions that are needed to actually run the models. Honestly, using one helper file for all 4 of these models was probably a terrible idea. I spent a lot of time debugging that helper file and finding inconsistencies in what the models wanted. This is a metrics output spreadsheet that my models output. And so here it gathers all the metrics, and you can see that some of the models are relating really well with a nice high R-squared value. And then other of the models are not only doing terrible, but terrible to a negative R-squared number, which I did find out is a thing. When I sort of looked at those models, they needed more data quality checks. It looks like maybe some bad data got through. And that bad data ended up really influencing the model to perform poorly. So again, this is a good model, and kind of output is proper. The curves are very similar to each other. And then this is one of the bad models with a negative R-squared value. I need to spend a good couple hours, good couple days trying to understand what went wrong here, because that is nowhere near it, and obviously not going to provide too much value for anyone. Future work. also think it would be interesting to add probabilistic values so that the operators can not just see what the load is, but the error bands for how far off the load may be. I certainly would do this with GPU resources in the future because that would make my life a lot better than sitting here staring at a model training a lot. And then there's more data. I don't think I got captured appropriately all of the drivers of the changes and so I need to add some more external signals. And I also would love, I forgot to ask LA for like some real-time signals, and then so I should add those in. And I think I am out of time.
Yep, that's correct. Thank you so much for your presentation. And yeah, I think we can make time for only one question. So if you guys have any question, please raise your hand.
Yes, Ms. Robinson.
Can you give me some security or adversarial risks that you may run into?
One more time.
Any security or adversarial risks?
I was actually kind of surprised that LA gave me access to all this data, but it came through a public records request, and they apparently had no problem with it. I don't think at this level there's very much security risk. It is rather aggregated. It's still pretty high up in the system. You can't identify individual customers or anything. And in the end, it's one of the beauties of a public utility is that we have access to data that sometimes would be hidden in private companies. So.
Well, you're using TFTs, it can be integrated into the smart grid.
Yes, and I think that's somewhat the hope is that it would help integrate some of that stuff. But yeah.
Okay.
Okay.
Good.
Thank you so much. Now we can go next with Trey.
Hey, how everybody doing? I do have a quick question. How do I get my slideshow on here?
So if you look up to the right corner on top, there should be a button that says share.
Okay.
It's a small screen with a pointing up arrow.
And then do I just click window or what do I click?
Yeah, and then choose the window that you want to share. Choose the window that has your presentation in it, and then you can. There we go.
Can everybody see it?
Yeah.
All right, cool. All right, so hey, how everybody doing? My name is Trey McElroy. I will be going over cybersecurity phishing detection tool, cultural and language differences. All right, so here we go. Let's see. I'm sorry if it sounds a little choppy, but all right. So the agenda, hello, welcome to my presentation on a topic that sounds a lot more exciting than it actually is today. I'll be discussing our journey in developing a phishing detection tool that pays careful attention to cultural and language differences. We have an action-packed agenda, so let's dive in. Just remember, if you start to feel like this presentation is dragging on, don't worry. There's a Q&A at the end, and I promise I won't bite unless you're a phishing email. I hope y'all got the joke on that. Okay. So, phishing emails. This is an introduction. Phishing emails have become a global threat, leveraging language and cultural nonsenses to deceive us. It's like a magician at a tech conference, fooling the crowd with clever tricks. Unfortunately, traditional detection tools are focused mainly on English, leaving many multilingual attacks undetected. The risk. If you're wondering what the risk is, it's like inviting a vampire to a blood bank. The risk gets, a little crazy. Phishing has become more sophisticated, prompting us to adapt our detection systems. Our goal is to create a multilingual detection system that can catch these sneaky emails, the little sneaky ones, in action so they don't go a little bit further than normal. The research and related work to establish a solid foundation, we analyze existing methodologies like decision trees, random forests, and support vector machines. Think of them as the three musketeers of email detection, each with their unique flair. We also explored the evolution of deep learning techniques in our field. It's fascinating how natural language processing can enhance phishing detection. It's just like taking a cooking class. You learn that the right ingredients can really spice things up. For the approach is understanding user requirements is critical. I conducted interviews and surveys to identify essential needs. It's like conducting a data survey to find out what people really want. Clear output and support for multiple languages, including Spanish and Arabic. And of course, I had to keep it user friendly. Nobody wants to handle a tool that feels like trying to untangle a set of earbuds from your pocket. That's kind of like the hardest thing to do right there. So for this right here, this is just a photo of what I imported into my phishing email website. I imported Nuppy, Panda, String, Seaborn, Matplotlib. It was really just a lot of documents that I imported so I can have the word knowledge ready for the phishing email detection. This is how it looks. It's welcome. Well, I actually changed the welcome to email phishing detector. I actually ended up changing that. I have a demonstration at the end, a video, so you can see. I didn't like that. That seemed kind of boring, like just a hey, hello, welcome to email phishing detector. So I kind of added a let's go fishing with the fish at the end. So just to spice things up. It's a layered architecture in composing data, pre-processing machine learning models, and a user interface. That's what it is. So right here, this is figure one, data pre-processing setup. We set up. I set up our text pre-processing using the relevant libraries. The transform text function we developed lowers the case of the input, tokenizes it, and filters out non-alphanumeric characters. It's like organizing a sock drawer, getting rid of the junk and keeping only what's useful. It's really just a vocab point right there. The implementation. During implementation, I gathered data sets containing multilingual phishing and legitimate emails, much like a collector of rare stamps. I made sure I had the best of the best. I pre-processed the data through normalization, stemming, and vectorization, basically giving emails a spa day before sending them off to model training, if any of y'all understand that. Figure two, in the data analyst, I plotted character links to explore the distribution of message links across phishing and legitimate emails. The green bars here represent legitimate messages and the red bars represent phishing ones. Interestingly, phishing emails often have fewer characters, probably because they know they've already lost half the audience with their terrible grammar. So yeah, I know it's a lot of jokes in this. I'm sorry. For testing and evaluation, I leverage key metrics like precision, recall, F1 scores, and gather user feedback. Early findings show improved detection rates across various languages. And the data analyst, explore the data analyst, EDA, I discovered common patterns and distinct features of phishing emails. I found frequent use of urgency-related words like account, verified, and urgent. It's like these emails are in a constant state of panic. Yeah. Well, that's figure 4. Visualization of suspicious words. These are suspicious words that can trap you. If these type of words get caught up in an email, it can easily be targeted and like hooked on a fishing rod as a phishing email. The findings. Initial findings are promises. I achieved high accuracy in classifying emails as phishing or safe with minimum false rates. I also learned that effective pre-processing techniques apply to our models like sunscreen on a summer day, necessary for avoiding burns. So for the conclusion, the tool offers a lightweight real-time phishing detection function. It's snappier than a toddler who just discovered their first chocolate chip cookie. The iterative development approach refined both usability and detection capabilities, and are excited about future enhancements that can tackle the ever-evolving phishing landscape. And for future work, looking ahead, I plan to enhance the detection abilities by integrating email metadata alongside contextual data points. And for the demonstration, so I don't know if you guys can see this or not. I hope you can. I'll play this one first. So this is everything I imported. This is the code that I used, Visual Studio Code with Python. Can you guys hear this or no? I don't know if you guys can hear it or not. Probably not.
Yeah,
So
Trey,
these
we
are.
won't be able to hear
this
it.
is the- You said you can hear it?
No, we can't.
Okay, so this is the imports. I've already talked about it. I just wanted to show some of the code that I did go through while doing it, and then this is the actual site right here. The Let's Go Fishing. I added the switched up and put the Let's Go Fishing with the fish, and that's the safe email. And then I just highlight pasted another text, which will can show you it'll respond as a possible phishing email. So that and yeah, that is really it. Yes, ma'am. I'm sorry, I can't hear you. Hold on.
Okay, sorry about that. So
Okay.
how does a tool distinguish between phishing and legitimate emails?
So there's
like with similar content.
there's keywords. It's kind of like using for easy example. So in one of the photos I showed, there's keywords that's suspicious words that can visualize if it's a phishing email or not. And these words are repetitive words, and it's kind of like using Chat GPT or whatever GPT AI you use. There's always a repetitive word where you know this person is using Chat GPT or AI. That's the same with the phishing email. You always know with these suspicious words because these words are repetitive, and it sets off an alarm once you use them.
Okay, does it analyze attachments? Like metadata, URLs?
I really don't know. The one I created, I'm not sure. I didn't try attachments or URLs. I will try attachments and URLs to find out. So that is definitely a flaw that I have because I did not think that far into it. I do apologize. I didn't think that. I'm not saying I didn't think that far into the assignment. I didn't think that far into like what about attachments, What about URLs? What about, I don't know, something else? All I thought about was emails when I was thinking about it. So I'm sorry.
That's okay.
That's a good question.
Thank you.
Thank you so much. I think that's it for today. Thank you to all the presenters. Great presentations.
All right, thank you.
So Harrison, who's next?
He was the last presenter.
I think that's it.
That's it, yeah.
So we have to go to the other sections then. There's another
It's the
section.
end.
Excuse
It
me?
should be done.
It's the end. It's 5:30 already. So
Okay.
yeah, we are all done with all the presentations.
Okay, thank you guys.
Thank
Appreciate it.
you.
Great. They were great presentations. So thank you very much.
Thank you so much.
Thank you. Thank you.
Good job. Take care.